All right, let's dive into a real scientific detective story. It's a puzzle that for decades seemed to break the fundamental rules of nature. And it all centers on this one seriously mysterious material, the quasicrystal. So imagine this. You have a material that is perfectly, absolutely ordered, but in a way that scientists swore up and down was completely impossible. That's the whole mystery here. What if a crystal could actually break the laws of physics as we knew them? And this really gets to the heart of the paradox. On the left, you've got a normal crystal. Think of it like wallpaper, right? It's an ordered pattern that just repeats over and over and over again. Simple enough. But on the right, you have a quasicrystal. It's also perfectly ordered, but with a mind-bending twist. Its pattern never, ever repeats. It's like a mosaic built on super strict rules, but it's still infinitely unique. I mean, how is that even possible? Now, this wasn't just some weird thought experiment. Nope, this became a real scientific puzzle that kicked off way back in 1984. For years, these things were just seen as this anomaly, this impossible crystal that totally defied explanation. This quote from the actual dissertation that inspired this whole explainer just nails the problem. Scientists knew these things were real. They could literally hold them. But they were completely stumped by the most basic question. What on earth were the atoms inside doing? How were they arranged to create this impossible, non-repeating order? So, how do you even begin to solve a puzzle at the atomic level? Well, you're gonna need some seriously powerful tools. This was the detective's toolkit that researchers brought to the table to peer into that tiny, hidden world. Okay, so the main tool for this investigation was the Analytical Transmission Electron Microscope, or TEM for short. The best way to think of it is as the ultimate magnifying glass. But instead of light, it uses a beam of electrons to see things right down at the atomic scale, giving researchers this incredible window into how materials are actually built. And it wasn't just one tool. They brought a whole suite of them. Now, don't worry about memorizing this list. The big takeaway here is that each of these techniques was like a different forensic test. One looks for chemical fingerprints. Another analyzes the structural patterns. Put them all together, and you get this deep, multi-angled investigation needed to finally crack the case. And all of that high-tech forensic work, it led to the first major breakthrough. It came from this really clever experiment where the researchers basically decided to see what would happen if they pushed a quasicrystal to its breaking point. The experiment itself was actually pretty straightforward. First, they started with a specific quasicrystal made of titanium, manganese, and silicon. Then, they just heated it up. It's a process called annealing. And when it all cooled down, the quasicrystal was gone. But in its place were 3 new, totally regular, repeating crystal structures. And that transformation, well, it held a secret. And here it is. This is the incredible clue they found. The new, normal crystals that formed, they hadn't forgotten where they came from. It was as if they remembered the strange, forbidden structure of the quasicrystal that was their parent. And here's the specific fingerprint they found. Icosahedral symmetry. Okay, think of a 20-sided die. That 5-fold symmetry is forbidden in normal crystals. Why? Well, it's for the same reason you can't perfectly tile a flat floor using only pentagons. It just leaves gaps. Yet this forbidden pattern was the signature of the original quasicrystal, and its ghost was still there in the new crystals. This clue, this was everything. It suggested that the basic building block of the quasicrystal wasn't destroyed, it was just rearranged. And that single idea let scientists build a completely new model to explain this whole puzzle. So here was the new hypothesis. What if quasicrystals aren't built atom by atom? What if they're built from these pre-packaged kits of atoms, specifically icosahedral clusters? These little 20-sided groups of atoms are the fundamental building blocks, and the quasicrystal is just what happens when you pack these clusters together in a way that never repeats. And you know what? This wasn't just a wild guess. The model worked. It worked beautifully.
It successfully predicted a whole range of really complex experimental data, everything from the weird diffraction patterns to the exact dimensions of those new crystal structures. The cluster theory, it connected all the dots.
Okay, so we have our building blocks, these icosahedral clusters. That's a huge step. But it kind of opens up a whole new can of worms. How do these things even form in the first place? And what about the messy reality of imperfections and disorder at the atomic level? How does that all fit together?
And that leads us to the final part of our investigation, finding those last few puzzle pieces. We need to understand how these bizarre materials actually grow and how they manage to build that bridge between total chaos and this perfect, non-repeating order.
So, being good scientists, the researchers first tested the existing theories for how disorder works in these materials. And when those didn't quite line up with what they were seeing, they introduced a new model, one based on the idea that the disorder itself isn't totally random, but is actually tied to imperfections within those fundamental atomic clusters.
And they found something absolutely fascinating when they studied how some of these quasicrystals form. For two of the systems they looked at, the atoms in the messy pre-crystal soup, that amorphous state, were already starting to arrange themselves into clusters that looked a lot like the final quasicrystal. The blueprint was there from the very beginning.
But then came the twist. When they looked at the classic original quasicrystal system, the one that started this whole thing, that similarity just wasn't there. For this material, the jump from chaos to order was way more sudden. And this proved there isn't just one simple rule for how all of these impossible materials come to be.
So, in the end, what did we learn from cracking this case? Well, this single investigation was a massive leap forward. It uncovered that hidden connection between quasicrystals and regular crystals. It gave us the powerful cluster model to finally understand their structure, and it showed us that even these strange materials have multiple, fascinating ways of forming. This work helped solve a puzzle that had scientists scratching their heads for years, turning an impossible material into one we could actually understand. And that leaves us with a pretty exciting final thought. If quasicrystals were out there, just hiding in plain sight and breaking all the rules we thought we knew, what other impossible materials are still out there, just waiting to be discovered?